All right, the title of this lecture is Electrical Basics and Terminology. Um, and again, it may seem like I'm jumping all over the place, like, okay, so we were doing nerve stuff, and then we got into diffusion for whatever reason, and now we're talking about electricity, like that's a physics or physical science concept. Yes, but if we don't have a general background on this, how nerves work is not going to make much sense. Okay? So let's start with the basic definition of electricity. Okay? Electricity is a form of energy resulting from the distribution and or flow of charged particles. And or flow of charged particles. And what I'm talking about when I say charged particles is subatomic particles, or specifically the two that have a charge. Which two subatomic particles have a charge? If you don't remember what I'm talking about by subatomic, I'm talking about the parts that make up an atom.
Protons and electrons.
Precisely. Protons and electrons. Because protons have a positive charge and electrons have a negative charge. Okay, so that is the general sense of what electricity is. Okay, but we need some other terms as well to help us understand what's going on here. And the first one, these are units. Okay, Joule is the first unit, and this is very simply a unit of energy. Ultimately, that's what you're paying for from the electric company, is them supplying joules of energy to your house. They don't call them joules because joules are very small quantities. The electricity you pay for your house is in another unit, just like joules. It's called kilowatt hours. Basically, you take the number of kilowatts multiplied by hours, and then you can get back to joules. But again, this is a very small quantity, and those are huge quantities. Now, and joules can measure not just electrical energy, they can measure motion, the energy from motion, they can measure energy from heat, a number of different things. The one we're going to spend the most time talking about is this one, volt, okay, or voltage. A volt is a unit of, and this one won't be quite as easy to make sense of, a unit of electrical potential. And what that is the difference in charge between two places. If there's a difference in charge between two places, that's considered to be a potential. And you're like, okay, I kind of get that. All right, let me use some practical examples. There is voltage that you could use to describe this. This is a AA battery. AA batteries, AAA batteries, C cell batteries, D cell batteries all have the same voltage. It's just that some of them can deliver that voltage for a longer period of time, and then some of them are smaller than others. It's actually printed right here on the side what the voltage is, but I can't zoom in, so I'll try to bring it closer to you. It's probably fuzzy though. Can you read what that says above my thumbnail?
1.5.
Yes, good. Okay, you can read it. AA's, AAA, C cell, and D cell batteries all supply 1.5 volts. You're like, well, why do some things require multiple of those? Because like this remote right here requires 2 batteries because it needs 3 volts to run. You just very simply add these together. I've got a keyboard in the cabinet that runs off of, you can use a 9-volt power supply, or you can put 6 of these in there. I think that math is right. 6 times 1.5 should equal 9, right? Yeah. So however many batteries is in there is what the voltage is required to run that thing. Well, the reason this has a voltage of 1.5 is because it has 2 terminals, okay? And there is a potential that exists between the 2 terminals. This end right here is your positive terminal. It has 1.5 volts. Okay, so I'll just draw this little battery right here. Okay, double A. This is the positive. I think that's right. Yep, there it is on the side. And this is the negative end. Okay, the positive has 1.5 volts right here on this terminal. And then this end right here, that terminal is 0 volts. So electricity will run through your appliance like this and power whatever appliance it is, and is returned. It has to make a loop like this. And the reason the electricity flows is because you have a difference in voltage. A difference of 1.5 volts is the potential. Now, it's a little bit different on rechargeable batteries. In fact, rechargeable batteries, for the most part, actually can't get to 1.5 volts, which is why some appliances or some tools say do not use rechargeable batteries for this, because they can only reach 1.3 volts each. But it really doesn't make a ton of difference for most of the stuff you're going to run. Then I could 9-volt battery, same song, different verse. Got a positive terminal and a negative terminal, but the positive terminal has 9 volts and the negative terminal has what? 0. Therefore, the voltage across, and anytime you talk about voltage, the next word in your mind should be the word across. The voltage across or between these 2 points is 9 volts. Let me use another example. Okay, in your house, you have these things on the wall, various places. Okay, there's a short one, a long one, and a roundish one. The roundish one is ground. You don't need it for everything, but that's 0 volts. If it's wired correctly, this one should also be 0 volts. That's your neutral. Okay, now I have an extension cord. Oh, hey, yeah, we could test this before we do. Make sure this battery's still good. I have a multimeter here somewhere. There we go. Multimeter is a fantastic tool. They're not that expensive. I think you can get one for less than $10 from Harbor Freight. But if you do anything with electricity, it's great. Or just to test batteries. So like here I have it set to where it's detecting about 1.5 volts-ish. And then let's test it. And I'll see if this battery's still good. I connect one to one terminal, one to the other terminal, and I've got 1.57 volts. So I've got, this battery is brand new. As long as it's above 1.5, it's good to go. Now, this may be a little more dangerous. I plugged this into the wall. Okay. Go ahead and dial 9 and 1, and we'll see what happens next. So, would you suspect that this is going to be less or more than 9 volts? What do you think? I'm hearing more. More, okay. Alright, so I jam this one in this side. Alright. You ready? Time to ride the lightning. I may have to wiggle them around a little to get them to connect. Oh gosh. Don't try this at home, kids. Why are you not? Oh, maybe I don't have it on the right setting. There we go. Oh, you can't see that. I have my hand covered up. 120 volts. Okay? That's because the difference between the left side and right side on this is 120, roughly. And I've got to wiggle it around here to try to get it to play fair, but yeah. And that's pretty steady. Okay. So that's because one side is 0, depending on how it's wired. Now, I'm not telling you that, number one, do not jam things into the outlet at your house. This tool is designed to be able to handle that. Okay? Number two, it's no guarantee that at your house, the short one will be the 120 and the long one will be the 0. They could have wired it up backwards. And most appliances will still work correctly like that, but yeah, don't take a risk. Okay. 120 volts. That's a pretty big number. How about this guy in your car? This giant battery under the hood. I say under the hood. In my wife's car, I went to look for it and it was not there. I'm like, where in the world? I had to look it up. A battery for the Buick Enclave is behind the passenger seat in the floorboard. Yeah. Now you still have terminals under. Yeah, I guess there wasn't much room in there, but like the terminals, you can still jump one from under the hood, but like to replace it, you had to pull it up. It was the prettiest battery I've ever seen when I replaced it because it didn't encounter all of the elements of living inside of an engine bay I mean, it was like inside the car. Now, would you think this number would be really high or really low or in between for this one, for the car battery?
Really high.
Why?
Just because it's a straight battery and it's like huge.
Yeah, it's a huge battery and it has to power the car. Basically, not power the car, but it has to provide enough electricity to turn the crankshaft of your engine against the compression to actually create, to get the car to start. So you think, man, that number's got to be huge. It's 12. I know that doesn't make any sense, okay? And the reason it doesn't, one of these is 12 volts and one of these is 0 volts. And if you were to go to Europe and try to plug in an appliance there, you need a converter because if you just plug your stuff straight into their wall, number one, it won't fit. And two, theirs, instead of being 120, is 240. Okay, yeah. I went to Portugal one time and somebody fried their like fan that they brought with them because they just got a thing that changed the plug, but it didn't change the voltage. So like their fan started smoking. Yeah.
I think in Ireland too, it's like that.
Yes, it is. Ireland and then in Asia, a lot of the rest of the world, they have a weird looking plug and it's 220 instead. Did you go to Ireland?
No, my parents did on that trip.
Okay. Yeah. Now, you're thinking, this doesn't make any sense. Okay, this is little, this is big, that makes sense, but why is this little? Okay? It's because of one other thing. You ready? It is this word, Ampere. Ampere is abbreviated as amp. So how many amps something has? An amp is basically the unit of electrical current. Basically, how much is flowing through. My physics 2 professor in college, he was very, very specific in how he used his words. He would say voltage across, he would say current through, and he never wavered from that. And it helped us get that in our minds too. So this kind of completes the equation, okay? Because, and I'm going to give you one more unit first here. Now I'll go ahead and spot you two. Okay? One you may have heard of also is the unit watt. A watt is a unit of power. And power and energy are almost the same, except power has to do with time. Okay? So power is energy over time. In other words, 1 watt equals 1 joule per second. So that's where watts play into this whole thing. I'm going to give you one more that we'll probably won't use at all in this class. I just want you to have exposure to it. And that is the unit ohm. An ohm is a unit of resistance. Resistance to current. Okay? Resistance to flow. If you've ever seen, these things here, I got a whole mess of them because I was doing some electrical projects. If you've ever taken apart anything electronic and you see these little things in it, those are called resistors. Their job is to take whatever electrical current is flowing and to slow it down or decrease it to a different amount, and that can change the voltage. Okay, so how do these all play together? How can 12 volts be in a car battery and 120 in the house and they both supply a lot? Here's how. These are the equations. Are you ready? First equation, and on the test, I will give you the equations. You won't have to memorize them, okay? The equation for power equals, you can't see that, equals current times voltage. Power equals current times voltage. Now, the way this is expressed is P equals I times V, or P equals IV. I don't know why current is I. That doesn't make a whole lot of sense, but it is, okay? So, let's use the car for an example. Your car battery only has 12 volts, but it has a lot of amps, okay? Let me tell. I'll pull it up here. When you buy a car battery, they'll be rated for what's called cold cranking amps. Okay, and typical cold cranking amps, you should probably expect somewhere on the order. So let me do this equation. So trying to figure out the power. Are you ready? Voltage of a car battery was what? 12. Okay, you ready? A typical car battery will have about 500 amps. Okay, so multiply this times this, and you end up with 6,000 watts of power that is supplied like that. Now, if you're driving a diesel truck, there's not just one battery, there are two. Because it takes a little better than double the power to crank a diesel engine than it does a gasoline engine. Because a gasoline engine, you're just building up a small amount of compression and then a spark ignites it. In a diesel engine, you have to force and create enough compression to get the diesel to the flash point where it basically explodes under the pressure. So you have to be able to crank with a lot more power. So there'd be 1,000 amps or more supplied from diesel batteries to start that truck. It's incredible. And of course, that would translate to 12,000 watts. Now, in a house, typically speaking, and I'm going to do one more of these here, power equals I times V. And in this case, we're going to do a calculation to figure out how much power one circuit in your house can stand, okay? And I'll put the limits in here. What did we say the voltage was in your house? 120 volts, okay? Now, the current, if you ever look inside the breaker box in your house, if your house has been wired somewhere in the last 20 years or even 40 years, they'll have little numbers on the switches. Unless your house is really old, then you won't even have switches. You'll have these things called fuses that look like little light bulbs that screw in. And that still works too, same idea. But the most common number you'll see on all those switches is the number 20. Because most of the breakers in your house are going to be 20 amp breakers. Because that's what Romex, 12 gauge Romex wire can safely send without overheating. So that means the maximum amount each circuit in your house should be able to do on power is 20 times 120. Yeah, 2,400 watts. That's why you're not going to run 2 microwave ovens on the same circuit at the same time. They will trip the circuit. You're not going to run more than 1 hot plate, or if your coffee maker and something else fires up at the same time, it can't handle very much wattage like that. Or my little kettle I have over here that heats up my water, it generates about 1,500 watts of power. Now there's one other little equation I want to throw in here too, and that's this. If you want to get energy back out, you've probably figured this out. Energy equals power times time. Energy equals power times time, because we can cancel out time in seconds. We can cancel out time very simply by multiplying by time. So let's say I was cranking this car right here for 5 seconds. So I take 6,000 watts and I multiply by, what did I say, 5 seconds? 5 seconds. And then I end up with, I used, in that case, for that 5 second crank, 30,000 joules of energy. So these equations are very, very simple. And like I said, I won't give you one on a test without, I will give you the equation if I have you do any of that stuff on a test, because this is not an electricity or even a physics class. But listen, it's important to me that you understand how all these things relate to one another, because we are going to deal a lot with this. Your nerves generate voltage, a measurable voltage. In fact, this is the reason an EKG works or ECG works at all. These leads are measuring the voltage that is going across your heart and how it changes, which is why there's spikes and dips and that kind of thing. And so we're going to look at, where does the voltage in nerves come from? How does it change as this stuff gets sent down the nerve? What does it mean to depolarize and things like that? But I wanted you guys to have a general handle on electricity before I did that part. So that's it for this lecture.